So let's look at some applications. Because functions really are all around you. You see them every day, you use them every day, and sometimes we take them for granted. They come in all forms. They come with verbal descriptions. They come in tables, also called tabular. They come in the form of graphs, often in newspapers and on websites. And they come in algebraic forms. And the algebraic forms are the least common format that we encounter in everyday life, but those algebraic rules are important, and we'll see some everyday examples where an algebraic rule is being used. We just don't see it written algebraically or with variables. Again, the verbal example is the most common form of an everyday function. Here's the rule for the function. Monthly cellular service is $39.95 for 400 minutes. After 400 minutes are used, the cost is 35 cents a minute for peak minutes. 7 a.m. to 9 p.m. weekdays, and 10 cents a minute for off-peak, and those would be the hours outside of the 7 a.m. to 9 p.m. That is a verbal function. If you have signed up for this program and another person has signed up for the exact same program, if you talk the same number of minutes, both peak and off-peak, your bills will be the same. If you use 300 minutes this month, your bill will be the same next month if you use 300 minutes. So you can depend on the rules not changing. This is an example of an everyday function. Our input would be the minutes used. And of course, we have to know when they're used, off-peak, especially if you go over, you have to know that. And our output is the total monthly cost for the service. So again, we have input, we have output based on a particular mathematical rule. That is a function. Here's an example of another everyday function. You go to the grocery store to buy some items. You scan those items. The rule is, after you scan them, add the total of all items and then add the appropriate sales tax. The output is the total amount you have to pay. That is a perfect example of a function. If you buy the exact same items as someone else, if your input is exactly the same as someone else's, then your output will be exactly the same, assuming that the rule, in this case a scanner cash register, is actually working properly and you can depend on it. Everyday function, input, output, mathematical rule, we just don't see it. The mathematics is programmed inside of that scanner cash register. We get tabular examples or examples in tables. And these are often used to organize large amounts of information, especially, again, in magazines, newspapers, and on websites. And so here's our function in the form of a table or a tabular function. And this is information I took directly from the Georgia Perimeter College website. And this information shows us a lot of data organized in a table. And a table is commonly used when you have this much information to display. And actually what we have here is the tuition for students who are enrolled in online classes at Georgia Perimeter. The input is the number of hours that the student takes. That's in this first column here. And the rule is shown here in the table, and our output is actually our total cost or our total tuition. And it's actually here in this last column. And then the rule for the function is indicated here along the way. And you can see that for 1 hour, it's $99 plus $250. There's a fee each time, a flat technology fee, a flat institutional fee each time. So it's the cost of the hours plus these fees. And it turns out that the cost of tuition, based on the number of hours X taken, is a pretty easy function to write if you're just taking online classes. And that is $99 per semester hour plus $250. Now, this is assuming that you're an in-state student. But this is just another example of how we see these functions every day, but we don't think about them as functions. But they really are, because they're rules that tell us, based on certain input values, what output values we should consistently or dependably get. Graphical example. And sometimes a picture says it well. In that last example, we really needed a table to display what was going on. But a graph can also display a lot of good information. So here's a function shown as a graph, and this is actually a picture of the S&P 500 stock returns since 1930 up to about 2000. And so I just want to pick one particular input value. 1961 is the input value that runs along basically your x-axis here. And then you've got your y-axis here, which is your output or rate of return. And it's about 11%. I'm just going to estimate. And this is a really interesting point along this graph, because this is where, because there's a peak in the investment here. You can see that it went up and it went down. It's gone up and down over the years, but we had a high point here. And sometimes we're interested in things like those high points and low points. Now, we do have a test called the vertical line test that we'll sometimes apply to graphs to decide if we have the graph showing a function or not. So this helps us to determine a function graphically. Here's what we know about the vertical line test. The vertical line test is used to determine if a graph is a function. To do this, we draw a vertical line anywhere on the graph. Now, remember, a vertical line is a perfectly straight up and down line. If we can draw a line on the graph, if it represents a function, when we draw this line on the graph, if the graph represents a function, it can intersect the graph at one point only. So here are several examples of graphs. Now, these are all graphs, but they don't all represent functions. So if we want to know if these graphs represent functions, we just draw vertical lines and see if we can touch the graph twice. If we can, it's not a function. Now, your line has to be perfectly vertical. It's a little hard for me to draw, but look, if we were to draw a perfectly straight up and down line here, it would cross more than once. So this is no, not a function. No, not a function. Yes, this is a function. Yes, this is a function. Pretend that these are vertical lines. And then again, we have a no. You can even see here right on the y-axis. So if you're given a graph and you're asked, is this graph a function? You simply draw vertical lines. And if you can cross the graph at more than one point, your answer is no, it's not a function. And if you can't, your answer is yes. Now, a quick explanation of that. Let's just take these 2 points here, for example. If I were to write these coordinates here, they would be 0, 0, and 0, 3. Here's why it fails the rule for or definition of a function. For each input, there can be one and only one output. One and only one output. But look here. For the input of 0, there are 2 outputs. One time there's a 0, one time there's a 3. It's like a drink machine where you press the same button, but it delivers 2 different drinks. It's not consistent. It's not dependable. Now, it doesn't mean it's not a valid mathematical thing or that it's not a true graph. It's just that it doesn't meet the definition of a function. So failing the vertical line test means that for one input, you've got different outputs. And that's why the vertical line test can quickly tell us whether or not our graph represents a function. Lastly, let's take a look at algebraic examples. These are the ones we'll use most often in this book. These are the ones that are used most often behind the scenes to run everyday life. These are the formulas that are programmed into our cash registers, into our gas pumps, into our cell phones, anything that has to consistently deliver the same thing based on the same input. That's a function. And so here's some algebraic examples of that same thing. We'll be using these algebraic models based on past data to predict future trends. It's the common use of an algebraic function. So here's an example where data is described with an equation. This is actually a graph I took from the internet on incarceration rates under the state and federal jurisdiction per 100,000 of the population from 1925 to 2008. We've got actually 3 graphs or functions going on here, one for males, one for females, and then the general incarceration rate out of 100,000. I made a model using my calculator, something you will learn to do later. I picked just 4 data points, which I've graphed along one of the graphs for males here. Here they are in my calculator. Again, you'll learn to do this yourself a little bit later. I've estimated those values to be 1925, a value of 150, 1955, a value of 210, 1984, a value of about 375, and in 2000, a value of about 925. Now, don't worry too much about where I got these values here. We will talk about this later as we go forward. I just want you to see that. I used the calculator to help me find a model that would predict the values along this curve, and I specifically looked at the male data only. I did what was called an exponential regression. You'll learn which kind of regression to do, when to do it, why we do it, and I came up with a model. 127.25 times 1.023 to the x. Now, why is a model important? Well, let's say I want to go out here to 2020, and based on past indicators, I want to know how many prisons I need to build in the state of Georgia or in the United States in order to, if the trends continue, in order to accommodate the prison population. So as a urban planner, somebody who works for the government, somebody who works for a school system, anyone who is gathering data, how many cars are going to be on the road, all kinds of information that we gather, we have to make these mathematical models to help us predict what will happen in the future, even though the model does not necessarily always work, because things change. Things get worse, things get better. Money's available, money's not available. Populations change. All kinds of things happen that could cause this trend line or these trends to change. But based on what we know now, what can we predict about the future? And this is a model that would help us to make that prediction. It turns out X is the number of years after 1925, because that's the base year that I used when I made my model. You'll notice 1925 was the first year. That's why this 0 here stood for 1925. And it's on the y-axis, if you want to call this the y-axis and this the x-axis. And so this is strictly a model. It does not generate these values exactly, but it can help me to predict the values along this curve, and even more importantly, I can use it to predict what's going to happen out here in the future. So these mathematical models are very, very important. Initially, you'll be given these kinds of models, and you'll just use substitution of your input value to figure out what the output value is. So if for a certain year X, for example, if I want to know the year, let's see, we went all the way to 2000. This is 2008. Let's say I want to know let's do 2020. If I want to know the predicted number of inmates in 2020, I need to subtract these to get X is 95. I would put the 95 in my model here, raise 1.023 to the 95 power, multiply that times 127.25, and that would give me the predicted population those number of years out in the year 2025. We might also be asked to locate a specific point along our graph and interpret its meaning in the context of the problem. So here's that same model I was telling you about. X is the number of years after 1925. Y is the incarceration rate for males, because if you remember in my previous example here, I was using the blue curve, which was for males only. So this data is valid only for males. So what I would have to do to find this value is substitute in for X the value 45. Do some arithmetic on my calculator. I would not do this by hand. Enter it on the calculator. 127.25 times 1.023 to the 45. Now, this needs to be done first, but your calculator, if you're using a scientific calculator, knows to do this first. That is that order of operations you've probably learned. Do parentheses, exponents, multiply and divide from left to right, add, subtract from left to right. So the calculator, a scientific calculator, knows to do the exponent before the multiplication. So let's do this and come back and find that point on the graph. Turns out to be about 354. Now remember, this is a model. This is not the exact amount by any stretch of the imagination, but if our base year was 1925 and we're looking at 45 years, because we're looking for f of 45, we're actually looking at 1970. 354, somewhere 1970, according to the model, would have been up here at about 354. So you can see that models are not always perfect. But you can use the model to find f of 45, and then we can talk about later why the model may not have been as accurate for that year as it needed to be. Maybe, in fact, I didn't use the right kind of model when I created my model. Don't be too concerned right now about where the model came from, how to get the model. Just think about input values and output values, function rule, and that a function has to be dependable.